Rational trigonometry is a proposed reformulation of metrical, planar and solid geometries by Canadian mathematician Norman J.Wildberger, currently an associate professor of mathematics at the University of New South Wales. His ideas are set out in his 2005 book Divine Proportions: Rational Trigonometry to Universal Geometry. According to New Scientist, part of his motivation for an alternative to traditional trigonometry was to avoid some problems that occur when infinite series are used in mathematics. Rational trigonometry avoids direct use of transcendental functions like sine and cosine by substituting their squared equivalents. Wildberger draws inspiration from mathematicians predating Georg Cantor's infinite set theory, like Gauss and Euclid, who he claims were far more wary of using infinite sets than modern mathematicians. To date, rational trigonometry is largely unmentioned in mainstream mathematical literature. Approach: rational trigonometry follows an approach built on the methods of linear algebra to the topics of elementary geometry. Distance is replaced with its squared value and angle is replaced with the squared value of the usual sine ratio associated to either angle between two lines. The three main laws in trigonometry, Pythagoras' theorem, the sine law and the cosine law, given in rational form, are augmented by two further laws, the triple quad formula and the triple spread formula, giving the five main laws of the subject. Rational trigonometry is otherwise broadly based on Cartesian analytic geometry, with a point defined as an ordered pair of rational numbers and a line as a general linear equation with rational coefficients, and by avoiding calculations that rely on square root operations giving only approximate distances between points, or standard trigonometric functions giving only truncated polynomial approximations of angles, geometry becomes entirely algebraic. There is no assumption, in other words, of the existence of real number solutions to problems, with results instead given over the field of rational numbers, their algebraic field extensions, or finite fields. Following this, it is claimed, makes many classical results of Euclidean geometry applicable in rational form over any field not of characteristic to. The book Divine Proportions shows the application of calculus using rational trigonometric functions, including three-dimensional volume calculations. It also deals with rational trigonometry's application to situations involving irrationals, such as the proof that Platonic solids all have rational spreads between the faces. Quadrants. Quadrants and distance both measure separation of points in Euclidean space. Following Pythagoras' theorem, the quadrants of 2 points in a plane is therefore defined as the sum of squares of differences in the coordinates. Unlike vector addition of distances with line segments, adding the quadrants of two vectors to obtain their combined magnitude always entails finding a third leg of the associated triangle they form, including collinear segments as a special case of degenerate triangle where the same calculation made with distance vectors simplifies to addition. In effect, the triangle inequality is modified under rational trigonometry to a symmetric form, equivalent to Pythagoras' theorem. Quadria spread. Spread gives one measure to the separation of two lines as a single dimensionless number in the range for Euclidean geometry. It replaces the concept of angle but has several differences from angle, discussed in the section below. Spread can have several interpretations. Trigonometric. It is the sine ratio for the quadrants in a right triangle, and therefore equivalent to the square of the sine of the angle. Vector. As a rational function of the directions of a pair of lines where they meet. Cartesian. As a rational function of the three coordinates used to ascribe the two vectors. Linear algebra. A normalized rational function. The square of the determinant of two vectors divided by the product of their quadrants. Calculating spread. Trigonometric. Suppose two lines 1 and 2 intersect at the point A as shown at right. Choose a point BA on 1 and let C be the foot of the perpendicular from B to 2. then the spread S is vector slope. Like angle, spread depends only on the relative slopes of two lines and is invariant under translation. So given two lines whose equations are and we may rewrite them as two lines which meet at the origin with equations, and in this position the point satisfies the first equation and satisfies the second, and the 3 points and forming the spread will give 3 quadrances. The cross law, see below, in terms of spread is, which becomes. This simplifies, in the numerator, to giving. Then, using the important identity due to Fibonacci, the standard expression for spread in terms of slopes of two lines becomes Cartesian. This replaces with and the origin within the previous result. Spread compared to angle. Unlike angle, which can define a relationship between rays emanating from a point by a circular measure parametrization, and where a pair of lines can be considered 4 pairs of rays, forming 4 angles, spread is a fundamental concept in rational trigonometry, describing two lines by a single measure of a rational function being equivalent to the square of a sine of the corresponding angle theta. The spread of both an angle and its supplementary angle are equal. Spread is not proportional, however, to the separation between lines as angle would be, with spreads of 0, 1/4, 1/2, 3/4, and 1 corresponding to unevenly spaced angles 0, 30, 45, 60 and 90 degrees. Instead, two equal, coterminal spreads determine a third spread, whose value will be a solution to the triple spread formula for a triangle with spreads even, giving the quadratic polynomial, and solutions, or this is equivalent to the trigonometric identity of the angles and of a triangle, using to denote a second spread polynomial in. Tripling spreads likewise involves a triangle with one spread of and obtaining a third spread polynomial in. This turns out to be. Further multiples of any basic spread of lines can be generated by continuing this process using the triple spread formula. Every multiple of a spread which is rational will thus be rational, but the converse does not apply. For example, by the half-angle formula, two lines meeting at a 15 degrees angle have spread of, and thus exists by algebraic extension of the rational numbers. Turn and co-turn twist spread polynomials. As seen for double and triple spreads, the nth multiple of any spread gives a polynomial in that spread, denoted as one solution to the triple spread formula. In the conventional language of circular functions, these nth degree spread polynomials, for any equals 0, 1, 2, can be characterized by the identity. Identities explicit formulas. From the definition it immediately follows that recursion formula relation to Chebyshev polynomials. The spread polynomials are related to the Chebyshev polynomials of the first kind, Tn by the identity. This implies the second equality above follows from the identity on Chebyshev polynomials. Composition. The spread polynomials satisfy the composition identity coefficients in finite fields when the coefficients are taken to be members of the finite field A. Then the sequence Sn, n equals 0, 1, 2, of spread polynomials is periodic with period 2. In other words, if k equals 2, then Sn plus k equals Sn, for all n. Orthogonality. When the coefficients are taken to be real, then for nm, we have for n equals m, the integral is pi 8 unless n equals m equals 0, in which case it is pi 4. Generating functions. The ordinary generating function is the exponential generating function is differential equation. Sn satisfies the second-order, linear non-homogeneous differential equation. Spread periodicity theorem. For any integer s and any prime p, there is a natural number m such that Sn is divisible by p precisely when m divides n. This number m is a divisor of either p minus 1 or p plus 1. The proof of this number theoretical property was first given in a paper by Xuzhang Guo and Norman J.Wildberger. It involves considering the projective analog to quadrants in the finite projective line P1. Table of spread polynomials with factorizations. The first several spread polynomials are as follows. Laws of rational trigonometry. Wildberger states that there are 5 basic laws in rational trigonometry. He also states that these laws can be verified using high school-level mathematics. Some are equivalent to standard trigonometrical formulae with the variables expressed as quadrants and spread. In the following 5 formulas, we have a triangle made of 3 points A1, A2, A3. The spreads of the angles at those points are S1, S2, S3, and Q1, Q2, Q3. The quadrants of the triangle sides opposite A1, A2, and A3, respectively. As in classical trigonometry, if we know 3 of the 6 elements S1, S2, S3, Q1, Q2, Q3, and these 3 are not the 3's, then we can compute the other 3. Triple quad formula. The 3 points A1, A2, A3 are collinear if and only if, where Q1, Q2 and Q3 represent the quadrants between A1, A2 and A3 respectively. It can either be proved by analytic geometry or derived from Heron's formula, using the condition for collinearity that the triangle formed by the 3 points has 0 area. Prove the line has the general form, where the parameters a, b and c can be expressed in terms of the coordinates of points a and b as so that everywhere on the line, but the line can also be specified by 2 simultaneous equations in a parameter t, where t equals 0 at point A and t equals 1 at point B, or, in terms of the original parameters. And if the point C is collinear with points A and B, there exists some value of t, call it lambda, for which these 2 equations are simultaneously satisfied at the coordinates of the point C, such that, and now, the quadrants of the 3 line segments are given by the square differences of their coordinates, which can be expressed in terms of lambda, where use was made of the fact that, substituting these quadrants into the equation to be proved, now, if and represent distinct points, such that is not 0, we may divide both sides by Pythagoras' theorem. The lines A1, A3 and A2, A3 are perpendicular if and only if, where Q3 is the quadrants between A1 and A2. This is equivalent to the Pythagorean theorem. There are many classical proofs of Pythagoras' theorem. This one is framed in the terms of rational trigonometry. The spread of an angle is the square of its sine. Given the triangle ABC with a spread of 1 between sides AB and AC, where Q is the quadrants, i.e., the square of the distance. Prove. Construct a line AD dividing the spread of 1 with the point D on line BC, and making a spread of 1 with DB and DC. The triangles ABC, DBA and DAC are similar. This leads to 2 equations in ratios, based on the spreads of the sides of the triangle. Now in general, the 2 spreads resulting from dividing a spread into 2 parts, as line AD does for spread CAB, do not add up to the original spread since spread is a nonlinear function. So we first prove that dividing a spread of 1 results in 2 spreads that do add up to the original spread of 1. For convenience, but with no loss of generality, we orient the lines intersecting with a spread of 1 to the coordinate axis, and label the dividing line with coordinates and then the 2 spreads are given by, hence, so that, using the first 2 ratios from the first set of equations, this can be rewritten, multiplying both sides by QED. Spread law for any triangle with non-zero quadrants. This is the law of sines just squared. Cross law for any triangle. This is analogous to the law of cosines. It is called cross law because the square of the cosine of the angle is called the cross. Triple spread formula for any triangle. This relation can be derived from the formula for the sine of a compound angle. In a triangle we have, equivalently, it describes the relationship between the spreads of 3 concurrent lines. As spread is unaffected when the sides of a triangle are moved parallel to themselves to meet in a common point. Knowing two spreads allows the third spread to be calculated by solving the associated quadratic formula, but because two solutions are possible, further triangle spread rules must be used to select the appropriate one. Trigonometry over arbitrary fields. As the laws of rational trigonometry give algebraic relations, they apply in generality to algebraic number fields beyond the rational numbers. Specifically, any finite field which does not have characteristic 2 reproduces a form of these laws, and thus a finite field geometry. The plane formed by a finite field is the Cartesian product of all ordered pairs of field elements, with opposite edges identified forming the surface of a discrete torus. Individual elements correspond to standard points, whereas lines are sets of no more than points related by incidence plus direction or slope, given in lowest terms that wrap the plane before repeating. Example: the figure shows a triangle of 3 such lines in the finite field setting F13 times F13. Each line has its own symbol, and the intersections of lines is marked by 2 symbols present at points. And, using Pythagoras' theorem with arithmetic modulo 13, we find these sides have quadrants if 2 plus 2 equals 50, 11 mod 13, 2 plus 2 equals 82, 4 mod 13, 2 plus 2 equals 128, 11 mod 13. Rearranging the cross law gives separate expressions for each spread, in terms of the 3 quadrants. 1 minus 2, clarified, equals 1 minus 3/7, 8 mod 13. 1 minus 2, clarified, equals 1 minus 12/3, 10 mod 13. 1 minus 2, clarified, equals 1 minus 3/7, 8 mod 13. In turn, we note these ratios are all equal, as per the spread law. 8/11, 10/4, 8/11. Since first and last ratios match, we just cross-multiply, and take differences, to show equality with the middle ratio also. Minus 78. Otherwise, the standard Euclidean plane is taken to consist of just rational points, omitting any non-algebraic numbers as solutions. Properties like incidence of objects, representing the solutions or content of geometric theorems, therefore follow a number-theoretic approach that differs and is more restrictive than one allowing real numbers. For instance, not all lines passing through a circle's center are considered to meet the circle at its circumference. To be incident, such lines must be of the form, and necessarily meet the circle in a rational point. Computation, complexity and efficiency. Rational trigonometry makes nearly all problems solvable with only addition, subtraction, multiplication or division, as trigonometric functions are purposefully avoided in favor of trigonometric ratios in quadratic form. At most, therefore, results required as distance can be approximated from an exact valued rational equivalent of quadrants after these simpler operations have been carried out. To make use of this advantage, however, each problem must either be given, or set up, in terms of prior quadrants and spreads, which entails additional work. The laws of rational trigonometry, being algebraic and exact valued, introduce subtleties into the solutions of problems, such as the non-additivity of quadrants of collinear points or the spreads of concurrent lines absent from the classical subject, where linearity is incorporated into distance and circular measure of angles, albeit transcendental techniques, necessitating approximation in results. Additional complexity is also introduced by the need to have rules to handle the dual solutions these quadratic relations generate.